All right, welcome everyone to today's edition of the Chemie Faculty Colloquium or Department Colloquium. Today our speaker is Pelayo, who I know from my days at the University of Toronto. He did his PhD at the Institute of Photonic Sciences in Barcelona, and he'll be joining there as a group leader in the beginning of next year, I believe. And today he'll tell us about his research in the field of materials science, specifically materials transformation for energy applications. So thank you for joining us, and please take us away.
Thank you, Tom. I'm really happy to participate in this series of talks. This is a very nice initiative, and I'm very glad to be here. So I am Pelayo. I have been for the last 5 years and a half working at the University of Toronto as a postdoctoral researcher. And that's where I had the privilege of meeting Tom, who has been an excellent scientist and an even better colleague and person. So yeah. So I'll talk in the next 20-30 minutes or so about some of our latest research in the field of materials designed for CO2 electrolysis. Just use some minutes to give a bit of context, although I'm sure that you're already aware of this problem that we face. So the world consumes around 18 terawatts per year of energy. And just to translate this into more mundane numbers, this corresponds more or less to every person in the world charging around 7,000 full charges iPhone batteries per person per day around the world, or just people boiling 70 kettles per hour all day around the world as well. So just we are a very energy intensive society, and we get most of our energy from fossil fuels. And this represents a problem because the way we extract these fossil fuels and the way we process these fossil fuels to generate the materials we need to generate energy, to generate fuels, or to generate feedstocks that are used for construction or for our use in society, generate a lot of CO2. This is in contrast with the availability of solar energy, for example, which you could see in this diagram represents a virtually infinite source of energy, which unfortunately is intermittent. Most of the CO2 emissions come from the manufacturing of materials and from fuels. You could see in this plot different chemicals and the corresponding greenhouse equivalent emissions. The most important chemicals you could see here, perhaps in terms of carbon footprint and both almost production volume, are ammonia, which is has a very large carbon footprint. You can see the ammonia here also has a different axis, so it has like a very high carbon footprint. But also of interest is the case of ethylene, which is a very important material in the manufacturing of plastics, for example, methanol and others as well. A way to alleviate this problem, a way to reduce the large volume of carbon emissions of these chemicals that we need, is to solve two problems at the same time. So I've shown you before that we had a lot of access to renewables such as solar, but this source of energy is intermittent. We could find a way of storing this intermittent energy in the form of chemical bonds by using solar electrons or hydro or wind to transform a liability such as CO2, which is bad for climate change, and water, using a process called CO2 electrolysis, where CO2 molecules, water, and electrons are combined together and transformed into value-added products such as carbon monoxide, methanol, ethylene, and other products that we have seen in the previous slide. So we can fabricate in this way materials that we need, materials that are based on carbon, using carbon dioxide. To do so, it's important for this process to be efficient, both from an energy, climate, and economical perspective, it's important that the materials that drive this transformation, catalysts that transform CO2, water, and electrons into these desired products, achieve different performance metrics. And in case that you weren't aware of what these performance metrics are, I just summarized here very briefly some of them. One of the important metrics is selectivity, which translates into Faraday efficiency, which is a measure of how many electrons are used to transform within the product mix, the molecule, the number, okay, how many of the electrons used to drive this transformation are used in the transformation to the right molecule, the molecule that you want. As you've seen in the previous slide, that there are many different products that you can obtain from CO2 electrolysis. So it's very important that you are very selective in this process. It's very important that you have a high selectivity and hence a high Faraday efficiency. You also want this process to be very active, so to have a very rapid transformation, so you can generate a lot of product. And this is important, especially in terms of cost, in terms of techno-economical analysis. It's very important for this process to be energy efficient. And this, I mean, besides the obvious thing that you want to be energy efficient, this is very important in this technology because the cost of this technology is determined to a large extent by the cost of electricity. So you want to make the best use of your electrons in this transformation. Last but not least, this has to be stable, obviously, over long periods of time for this to be interesting. In this slide, I present what the state of the art today is in terms of these metrics compared to the targets that are desired for the economic viability. So for these systems to be profitable with the current picture, the current numbers that we have for the cost of CO2, the cost of electricity, and the cost of these systems, and compare this also with like a more mature technology such as PM electrolyzers, which are rather similar in some sense. So you could see here how ethanol and ethylene, which are only two products, but these findings, I mean, these numbers translate in general to a lot of other products as well, are still far in terms of these metrics to the desired target. So we still have work to do to improve these figures of merit. Faraday efficiency or selectivity is actually one of the figures of merit that has improved more during the last years and is close to the targets, as well as the partial current density, especially in the case of ethylene, which has surpassed even the expected targets of operation. But what now is missing, and it's very important actually, is the energy efficiency, which is far from the targets needed, and very especially important is the operating lifetime, which is far behind from the targets desired. And how would you try to achieve these targets? So one approach, I mean, one part of the system, an important one, but not the only important part, is the catalyst. So the catalysts are the materials that drive these transformations. And in order to tune this catalyst, in order to be selective, so in order to have the right product and to have it at the cheapest use of electrons, to have it to be energy efficient, there are different materials properties that one could tune, such as facets, such as coordination of atoms in the catalyst, structure, dopants. In some, there are a lot of degrees of freedom in material design to tune this catalyst in such a way that by tuning this catalyst, you tune the way these materials interact with CO2 molecules, with water, with electrons, and with the reaction intermediates that proceed along the reaction pathway to the desired product. One big problem is that even though you have a lot of degrees of freedom, when you put these materials into an electrolyzer and you operate them, it doesn't matter that you design the best material, the best catalyst for the reaction that you want. It's very often the case that these materials transform themselves and they do very very strongly. So you could have a material with the right facet that transforms into the wrong facet. You could insert dopants into your material, which would agglomerate and then would lose the effect that you desire. So this is the outline of my talk today. I'll just start by talking about one work we carried out a year and a half ago, approximately, which focuses on this problem, focuses on understanding how materials reconstruct, how catalyst reconstructs during operation, and how to drive this transformation so that you end up achieving the desired structure while these materials are actually doing their job. I will then talk about other more recent works in which we looked into improving the activity of these catalysts using hybrid material combinations involving the use of metals and ionomers to control how CO2, how water, and how electrons interact in the vicinity of the catalysts. So just in the case of catalyst reconstruction, so a while ago we're interested in bismuth as a catalyst for CO2 electroreduction. Bismuth is an interesting catalyst for the transformation of CO2 into formate. But bismuth exhibits a remarkably strong facet dependence in terms of performance. So if you have one facet, you could have instead of having CO2 reduction into formate, you might very well have not have CO2 reduction, sorry, but have a competing reaction, which is hydrogen evolution from the water-based electrolyte. So we began by modeling the dependence of these facets using DFT. So we sampled the symmetric binding sites on the surface of this catalyst, both for the HER, which is the competing reaction, and CO2 reduction into formate. We identified the rate-limiting step to be the proton-electron coupled transfer to the HCO intermediate on the surface. And what we found was that bismuth 110 facets offered a near optimal Gibbs free energy for formate evolution. This is minus 10 millielectron volts, so it's close to the thermodynamic minimum, and this gap is remarkably larger compared to the case of other facets such as bismuth 121. So in this case, CO2 evolution will be CO2 reduction will be much more favored compared to hydrogen evolution. So you have a lot of these facets, you would promote the transformation of CO2 into formate. But this is difficult because normally, as I said before, materials pre-catalysts, as they are often called, based on bismuth, tend to transform into a variety of facets, which might not necessarily include the desired 110 facets. So in this work, we utilized a material platform consisting on two-dimensional bismuth oxyhalides to template catalyst reconstruction in such a way we could achieve the desired final arrangements regarding the facet distribution. So we made this pre-catalyst by dissolving metal halide salts in polar solvents such as DMSO, and then we blade coated this ink onto a carbon paper. When we then hydrolyze this substrate into an electrolyte solution, we obtain this kind of structure consisting of two-dimensional layers of bismuth oxybromides. These materials themselves are kind of amorphous, and they exhibit a plurality of facets, as shown here in HR high-resolution TM microscopies. But interestingly, when you run these materials, so when you put this catalyst into the system under reducing conditions, you see that these materials transform, which is very clearly seen with SEM. You see like this rather amorphous pre-catalyst ends up transforming in some kind of petal-like bismuth substrate. And interestingly, after this process has taken place, we could only observe bismuth 110 facets in this higher resolution TM. So in this way, we assessed the catalyst before operation and after operation, but we didn't know yet what was going on during operation, which is what we care about the most. So then we were lucky to have some time in the Canadian Light Source synchrotron, and we performed GWAS, grazing incidence wide-angle X-ray spectroscopy experiments in a custom-made cell. So you could see here the GWAS map of these materials in open circuit, while in the custom sale, and there is a remarkable change in the GWAS patterns when we subject these catalysts under a negative reduction potential. You see like the distribution of the peaks and all the features are remarkably different. So in here, you could see the GWAS patterns along this axis, which is where we observe that that's the most important one. And you could see like before we perform the reduction, so before these materials actually did their job, you could see a very kind of complex distribution of peaks which correspond to different elements such as bismuth 110, which is the ultimate facet that we want, but also 121 facets, 112 facets, and also facets corresponding to bismuth oxybromides and bismuth oxides. What was interesting was that once we first immerse this substrate in the electrolyte, and moreover, when we apply a reducting potential, we see a total redistribution of these peaks. So we see a disappearance of the peaks corresponding to oxide species and even to oxybromide species, meaning that the bromides have leached out of the catalyst. And interestingly, we see a dominant appearance of the facets corresponding to 110. When we measure this catalyst into an H cell in a neutral electrolyte, we observe that the current density, which is a proxy for activity, is improved in bismuth oxybromide derived samples compared to bismuth samples. And this extends for a range of potentials as well, where we observe that the dominant element that we generate in this potential range is formate. But we were not super happy yet because even though we can achieve high selectivity, this current density is not yet what one would desire for their systems. So we realized at this point, like as well as other groups in this field, that the current density in these CO2 electrolysis systems was limited by the fact that these catalysts were being operated in H cells, and in these cells CO2 is fed through a water-based electrolyte. So the transport of CO2 from the source to the surface of the catalyst is based on diffusion. So this is a mass transport problem, limiting the available currents for reduction, so the amount of available CO2 that could be transformed. So only currents below 50 milliamps per square centimeter, more or less, would be within reach. But if you implemented this catalyst in a so-called flow cell, where CO2 reaches the surface of the catalyst from the back of a hydrophobic substrate instead, so the path of CO2 to catalyst is much shorter, you could achieve much higher current density. So in doing so, we observed that we could keep extending the high selectivity towards formate towards up to higher current densities, so up to at least 200 milliamps per square centimeter. The catalysts were stable for at least 60 hours. And that concludes this chapter now. So now I'll just focus on a different topic here. So just following this translation of catalysts from H cells to flow cells in 2018, Tom here and his colleagues, they discovered that the performance of CO2 electron reduction in these kind of flow cells could be remarkably improved if this reaction took place in an alkaline environment. So by performing this CO2 reduction in a very basic electrolyte, you could suppress the competing hydrogen evolution reaction, and you could shift the onset potential for this transformation towards lower energies. So in this way, improving the energy efficiency of CO2 transformation, in this case towards ethylene. One of the problems of this, despite achieving a much higher selectivity and energy efficiency compared to previous systems, was that the fact that this is an alkaline environment limits the volume of the reaction interface. So CO2 can only penetrate within tens of nanometers into the catalyst before being transformed into carbonate, which is which is a downhill reaction. So CO2 will react with hydroxyl groups, hydroxyl anions in the surface of the catalyst and in the electrolyte, and then couldn't make it to other places of the electrolyte. So only this very abrupt region of the catalyst contributes to the desired reaction, and this part of the catalyst will only make a hydrogen instead. So you could see here how by increasing catalyst thickness, you start seeing a sharp decrease on the ethylene partial current density. So you can only have around 20 nanometers of effective catalyst. So we thought, how can we increase then the activity further, which is obviously desired. So one could think of increasing the intrinsic activity of the catalyst, of course, but that's rather difficult. Also, you could think of increasing the applied potential to increase the current, but in doing so, you would also increase the OH generation at the surface, actually making this problem even more important. So you have more potential, you have more OH, then you have even less carbon dioxide because it will get consumed in the surface. So we thought of a strategy that would allow us to retain the alkaline benefits, so to retain the high energy efficiency, but modifying the catalyst environment in such a way we could provide with increased CO2 availability without introducing problems of ion transport. So we started by modeling this. So we thought, okay, what about we had a layer on top of the surface of the catalyst where you had an increased availability of CO2, where CO2 could diffuse better than it would diffuse in a standard alkaline environment. So we observed that we could have a much higher available current if we improve the CO2 available, if we improve the diffusivity of CO2 compared to the diffusivity of CO2 in the alkaline electrolyte. So we could improve from having reduction currents of hundreds of milliamps to having reduction currents of amps. So then the challenge, of course, was how to implement this. And we found inspiration on the way membranes in cells work. So membranes, lipid membranes in cells consist of an amphiphilic layer where you have a very hydrophobic and hydrophilic domains in such a way you separate different worlds. And this structure, this molecular structure, is very similar to one old friend to the electrochemistry and catalysis community, which is naphion and more in general perfluorinated sulfonic acid ionomers, which consist of a backbone and a side chain of very hydrophilic groups and a head of a very hydrophobic group, sulfonic acid head. So our thinking was, can we control the way these molecules, these monomers assemble into a polymer, very thin ionomer layer in such a way you could achieve a similar arrangement. So in such a way you could have domains of hydrophilic and hydrophobic layers. So to do so, we started by, dissolving these ionomers, which for now on we focus in a particular type called naphion, in a polar solvent. So when you disperse these ionomers in a polar solvent, you promote the exposure of the ionic group, which is in this case sulfonic acid. So you have like micelles consisting of naphion molecules arranged in this way. So we spray cast this solution into a catalyst layer consisting of copper or silver, which was spattered on top of PTFE, and then we spray this ionomer. What we found interesting is that depending on the loading of the ionomer, we could see a very sharp difference in terms of the limiting current for the reactions that were taking place. In this case, just for simplicity, we started looking into the oxygen reduction evolution reaction in this potential range. So we fed oxygen, not CO2, we fed oxygen to the back of the gas diffusion layer. And in this potential range, there is no competing reaction. So only oxygen can get reduced into water, for example. So you see how by increasing the loading of the catalyst, we modify the limiting current. So you see like the current gets saturated here. This is what we call the limiting current. So just by adding a bit, you see a remarkable increase in the current density. And then if you put too much, you start seeing a decrease. So you are kind of limiting the access of the gas to the active sites of the catalyst. And very interestingly, we observe this difference in the oxygen reduction, but we don't see such a difference when the reactant of this reaction is not a gas, but it's water. So the reaction shows an improved current for ORR, but a similar current for HER. We characterize this catalyst. You could see here SCN images and high resolution TM images, and optimize them with curves. So you could see here that this ionomer layer is quite conformal over the fibers of this catalyst, over this copper catalyst in this case, and the thickness is within 10 nanometers. And this is a very important point, as we will show later. So you can see here the wide-angle X-ray scattering spectra of this catalyst. So we observed the presence of features characteristics of PFSA on these catalysts, and then we sought to characterize them under operation again. So we explore how we try to assess how these materials arrange onto the surface of the catalyst. And we did so by using SERS, surface enhanced Raman scattering, while the devices were in a customized cell. So interestingly here, we could see how, so this is the reference, the black line is the reference, this is the sample with the ionomer, and these are the peaks corresponding to perfluorinated groups and to sulfonic acid groups. And when the samples are hydrated and under operation, you see that the ratio between the features corresponding to a sulfonic acid and the perfluorinated acid groups, and the perfluoronic groups change in such a way that the relative intensity of these groups of sulfonic acid groups is higher, meaning that because the way SERS work, meaning that they are closer to the surface of the catalyst than these groups. So we believe, based on this, that these ionomer layers exhibit a preferred orientation where sulfonic acid groups are closer to the surface of the catalyst. We also perform in situ SERS during oxygen reduction. So you see here the current density versus potential for this reaction. You see a much higher current density for the case of the samples with ionomer, which also agrees well with the results we get in SERS, where we see an increased presence of surface oxygen for the samples of the ionomer with respect to the samples without the ionomer. We then have improved this kind of proof of concept enhancement of gas phase electrolysis, tried this mechanism for other reactions and other catalysts too. So we explore how silver ionomer and copper ionomer samples would lead to higher current densities. So in the case of silver, the main products, as you would expect for a silver catalyst, are CO2 and formate. You could see again here how the current density increases quite dramatically. And also for the case of copper, where we generate mainly ethylene and a bit of carbon monoxide. So you see that the limiting current density has changed from 50, 60 milliamps in this case to almost 600 milliamps in this case. So just to challenge what's going on here, and Tom, let me know if I'm running over time or yes, I see you are on camera. So
you're doing well for time.
Okay, so so there were different ideas that could challenge this hypothesis of increased CO2 availability. One is, are we just modifying the local environment or the local pH of the catalyst? Are we changing the way CO2 and carbonate reactions take place? Or are we modifying the electronic properties of the catalyst at a more fundamental level? So based on, we just to challenge this hypothesis, we ran 1 million experiments over a few months. And what we observed was that we see this phenomenon of enhanced gas electrolysis for different gases. So for oxygen, for CO, and for CO2. And only CO2 suffers from the CO2 carbonate, the so-called CO2 carbonate problem. So we disregarded this as the main difference in these catalysts. We also characterized this catalyst, and we observed that we had a similar electrochemical surface area, and the catalyst also exhibited similar contact angles. Meaning that they had the same hydrophilic, hydrophobic interaction with the electrolyte itself. All samples exhibited similar hydrogen evolution reaction currents, meaning that we only observed a difference in performance for gas-based electrolysis, and all of this happens across different electrolytes and pHs to a different extent, of course. And we didn't observe any enhancement in aqueous-based cells. So in aqueous-based electrolytes, such as H-cell, where CO2 is already limited by the solubility of the electrolyte. Interestingly, too, we performed some in situ XAS characterization, and we did observe that the coordination and the environment of copper atoms were similar. So there was not a difference in this sense in terms of electronic properties at the fundamental level. We were challenged as well by the reviewers since these ionomers, Nafion membranes are used in the community actually for the opposite problem. So just to preclude CO2 transport actually. And what we found, and what other groups found after our paper too, is that it's very important how these ionomers are arranged. So only if you are able to have a very thin layer of these ionomers, you could have a layer with not a lot of entropy, so where the domains are kind of parallel within each other in such a way that you could benefit from CO2 enhancement or gas transport enhancement compared to the bulk electrolyte. Whereas if you have a thick membrane, you will have a different arrangement of these ionomers in different domains. So in this way, you would preclude gas transport instead of benefiting gas transport compared to the bulk electrolyte. So I like to call this the lasagna versus spaghetti comparison, where lamellar distribution of these ionomers is leading to this enhanced gas transport. So just to take advantage of this further, we designed a 3D structure based on this catalyst. So we mixed the copper nanoparticles with these perfluorinated sulfonic acid ionomers, and we made which we call a 3-dimensional catalyst ionomer bulk heterojunction, in which we could increase the thickness further, extending the reaction interface further. You could see here the high resolution material mapping. You see here copper and you see carbon. So these dark elements are the copper nanoparticles, the copper catalyst, and this kind of gray layer corresponds to the ionomer kind of backbone skeleton. So you see there are percolating paths of copper nanoparticles that are needed to provide electron access to the catalytic sites, and percolating paths of these perfluorinic acid ionomers that are needed to provide water and also to provide gas transport to the surface of this catalyst. So just to optimize this, we increase the loading of these ionomers. So we could keep increasing the partial current density up to thicknesses of tens of microns. And if you remember in the previous slides, we've seen that in the absence of these ionomers, the maximum thickness that could contribute to the reaction was on the order of tens of nanometers. So here instead, we could benefit from increased activity up to 5 to 10 micron thickness. You see this, the black line is the total CO2 reduction current, the blue line is the current corresponding to C2 plus products, ethylene, ethanol, and the green line corresponds just to the current for ethylene. So we achieved here for the optimum thickness around 900 milliamps per square centimeter of ethylene. And just optimizing this further for the right thickness, we optimized the electrolyte, we ran 1 million samples and have statistics for this now. So the best Faraday efficiency towards ethylene is around 65 to 70%. And the partial current that we can achieve for the best samples is around 1.3 amps per square centimeter just for ethylene. The energy efficiency of this half reaction is around 45%. And this is high for this half reaction, but this not high enough yet. So the overall energy efficiency, including the cathodic and the anodic side, is around 20%. So this is still far from the needed 60% that's needed, I mean, for economic viability. So just to summarize, at this point, we can produce some products such as CO or ethylene with high activity using CO2. But the production of other elements such as alcohols, fuels, or more complex hydrocarbons is still sluggish. There is still a lot of things to do. There are still a lot of things to do regarding improving energy efficiency and stability. And a very important problem that I have omitted at this point is the fact that carbonate generation is a very important limiting factor in these systems, limiting the single pass utilization of carbon monoxide. So if you think of a system using very alkaline electrolytes such as 10 molar KOH, for example, you would realize that the energy efficient, including carbon electrolyte recycling and all of these aspects, doesn't make sense. So to make this technology viable, we need to translate these findings into systems that operate in a more neutral environment. And this is, for example, the case of systems involving a membrane electrode assembly cells, where CO2 is fed combined with water into the system, and there is not a catholyte. So the CO2 is not reacting in such a heavy way with this basic environment in such a way, leading to a lot of carbonate. So there are many interesting works that have been recently published in this field, and more are coming. I don't think I have time now to present some recent work that we have published in the last couple of months or so, but I will just conclude with the challenges that remain for MEA systems. So in MEA systems, I've been talking a lot about in situ experiments and how this enabled advancing these technologies. But for this kind of cells, this is very challenging because the way they operate and the lack of reference electrodes and other considerations. So it's definitely very, very important to develop operando techniques to enable assessing the system and catalyst performance in these MEA cells. I will just omit these slides for the sake of time. I will just thank all the group members of the Sarian group and the Sinton lab too, who made this works possible. And just to conclude, I'll just, as Tom mentioned in the beginning, I'll move to Barcelona next year. So this is the Institute of Photonic Sciences, which is located 20 kilometers south Barcelona, 5 minutes from the beach. It's a very new institute, born in 2002, but very successful institute with a lot of nice research groups, nice papers, nice collaborations with industry. So if you're interested in joining this institute and in joining my future group, I just have my email there, and we expect to hire for people in the next summer and fall. Thank you for your time, and I'm open to any questions.